Okay, let's continue the discussion of section 4.6. The bounds for analytic functions. Continue. Last time we stopped at a lemma of polynomial functions. The polynomial function says if you have a polynomial p of z equal to zn plus an minus 1, zn minus 1, and a1z, a0, a polynomial. Here, of course, n is greater than or equal to 1. It's not constant. And let a be the maximum of coefficient 1, opposite value of an minus 1, and opposite value of a0. Then for all z with opposite value greater than or equal to 2n times a. So a is fixed, determined by p, and n is also determined by p. So this is a constant number. So for the opposite value of z greater than or equal to 2n times a, we have the opposite value of a p of z is greater than or equal to 1/2 opposite value of z to nth power. So last time we proved this. Simply speaking, we just say that when n is sufficiently large, it is greater than at least half of the z to n, okay, with opposite value. And with this lemma in mind, we prove the following fundamental theorem of algebra. Fundamental theorem of algebra says every polynomial will have a 0 if that polynomial is non-constant, right? For every non-constant polynomial, it must have a solution. Fundamental theorem of algebra says it's a theorem 22. Every non-constant polynomial with complex coefficients has at least 1 0. Okay. Of course, we know that if you only talk about polynomial functions in real system, then in the set of real numbers, not every polynomial has a real solution, right? But for the complex polynomial with a complex solutions, then at least it has at least 1 if you do not have a constant polynomial. Okay, now let's see the proof. Suppose, so the theorem claim it has a 0. In order to prove it, we will assume it has no 0. Suppose that to the contrary, that p of z some polynomial an zn plus a0 is a non-constant polynomial course, non-constant n is greater than or equal to 1, having no zeros. Okay, so this function is a special function. It has no zeros. Of course, we are talking about a 0. Here, of an is non-zero. The leading coefficient is non-zero. Then we divide this whole equation by an. We will have the equivalent equation. Then we will have the same zeros. So without loss of generality, we always assume that an is equal to 1. This leading coefficient is always 1. If it's not 1, you divide the equation by this leading coefficient, and you don't change any property about the zeros. Okay, so since this polynomial, we assume it's not equal to 0. This P of z is not 0 for all z, then 1 over P of z, let's call it what? Do we have a name? No. 1 over z is analytic over c. It's analytic function over c. It's a differentiable everywhere. Analytic over c is an entire function. It's an entire function. So whenever you have a non-zero polynomial, the polynomial without a zero, then the reciprocal is going to be an entire function. Okay, we will show that. This 1 over P of z is bounded. P of z is bounded over c. How? We are going to apply the lemma we just proved. So for ops value of z is greater than or equal to 2n times a, the a is here. When we have such have such z, we have P of z greater than or equal to 1/2 z to n. So 1 over P of z ops value is going to be less than or equal to, so denominator becomes numerator, numerator becomes denominator. So it's a 2 over z to n, not 2. 2 over z to n. And z is greater than this, so it's less than or equal to 2 over 2na to nth power. Okay, so it doesn't matter what expression you have, this is a fixed number. A number. Okay. When it's outside a disk, you see here it means it's far from the radius. It's far from the origin. When it is far from the origin, it's always bounded. Ops value of 1 over p is always bounded. And this is the exterior part of the disk. So for ops value of z is less than or equal to 2n times a. This b center, b origin with this radius, this is with a closure, is a compact set. Remember, in the Euclidean space, let's put a Cn. In Euclidean space, a set is compact if and only if it is closed and bounded. Okay, a compact set means it's closed and bounded in the Euclidean space Cn, complex Euclidean space. And we also know that all continuous functions are bounded. If you have a continuous function, it's always bounded over a compact set. Okay, so that's what we need from the topology. Okay, so you have a compact set and you have an entire function. 1 over p of z is entire, of course, continuous over this b0 to n a, a continuous function over a compact set. So there is an m such that it is bounded. Upper value of 1 over p of z is less than or equal to m. Hence, for all z in this closed b0 to n a, hence the upper value of 1 over upper value of p of z is going to be less than or equal to m plus 2 over 2na to nth power for all z in C. Okay, so you have this bound for the closed disk. You have this bound for the exterior part of closed disk. You just simply put them together. We don't care how large this number is. We just care it is a fixed number. Right? Okay, so So 1 over p of z is a bounded entire function. It is constant. It's constant. This one is constant, so p of z is constant. Right. P of z is constant. This is a contradiction because we assume p of z is non-constant. We assume it's not constant. Therefore, p of z has at least 1, 0. Okay, so we finished the proof of a fundamental theorem of algebra. Fundamental theorem of algebra. So in the fundamental theorem of algebra, we just claim it has at least 1, 0. So for the p of z has a 0, z1. Let's call it z1. Then z minus z1 is a factor of p of z. So we study p of z over z minus z1. If it is a if it is non-constant, then there is a z2. There is a 0 z2. If this one is not constant, it means this ratio. If this ratio is non-constant, it has a 0 z2 by the same fundamental theorem algebra. Okay, then z minus z2 is a factor of p of z over z minus z1. And then you study p of z over z minus z1, z minus z2. You continue until P of z over z minus z1, z minus zn to be a constant. Okay, constant function, a constant number. This process must stop at a certain moment because here you have a degree. The polynomial have degree n, then you need n step in order to get a constant. Okay, so it's not an infinite process. It is definitely a finite process. Okay, so by this we can see that if the degree of P of z is n, then there are z1, z2, zn such that P of z is equal to a times z1 minus z minus z1, z minus z2, z minus zn. Okay. And this a is actually the constant in the final step. A is a constant number in the final step. Okay. And here z1, z2, z up to zn, they may be repeated. They may be repeated. Okay. So that's why we say all the complex functions can be factored as a product of linear factors, because of this fundamental theorem of algebra. Okay, so that's actually the application of Liouville theorem. When you have a constant bounded entire function, it is constant. That's a Liouville theorem. Okay, now let's talk about the maximum modulus theorem. In order to talk about maximum modular theorem, let's go back to the Cauchy formula, integral formula. The Cauchy integral formula says f of z0 is 1 over 2 pi I integral over CR f of z over z minus z0 dz, where CR is z minus z0 equal to R. See. Okay, so z0, circle centered at z0 with radius R. This is z0, this is z. Okay. And of course we choose this counterclockwise orientation. So here z is z0 plus r e 2 pi I t. So t is between 0 and 1, between 0 and 1. So we must mention this orientation. It has to be counterclockwise, this orientation. Okay, of course with this realization we can do substitution. We will see that f of z0 is 1 over 2 pi I. Dz, check here, dz becomes r e 2 pi I t and times 2 pi I dt. dz is the derivative times the differential. Okay, and when we use this, we get from 0 to 1, f of z is f of z is this, z0 plus r e 2 pi I t. The denominator z minus z0 is equal to what? Is equal to r e 2 pi I t. This is the denominator. This denominator, check here, it is almost, let's not use 2 pi. If we don't have 2 pi here, then this is 2 pi. Okay, then there's no 2 pi here. There's no 2 pi here. Okay. This denominator, it will be cancelled with the with the derivative from the differential, so you don't see the denominator. Then you will have I dt 0 to pi. Here it becomes 2 pi. And I cancelled, so that's the reason we have 1 over 2 pi integral 0 to 2 pi f of z0 plus r e sorry, there's no 2 pi it r e I t I already cancelled dt. Okay, so this is a formula 4 in the on the page 165. Okay, page 4 165. And this is the equivalent formula like the as in the Cauchy integral formula, but this special representation is also called the mean value property. So what does it mean? So it's this input is z. Remember, this is z. So you have the value of z. You integrate function along the circle and divide by 2 pi. Then what you have? You have it equal to the value at the center. It's kind of your average. You average the boundary, you get the center. So that's why, because you see the average. So that's why it's called mean property. The average property of the analytic function along the circle. And from here we can see that if, well, it's one property, very important to keep this in mind. And if this f of z is bounded by m over CR, if you know that the function is bounded over the circle, then apply the triangle inequality and the property. You see, what I mean triangle equality is actually this one. Remember that when you put ops value and you move ops value into the integral, you have inequality. And this is less than m. You integrate m over interval 0 to pi and divide by 0 to pi, you get m. So if you know that the function around the circle is bounded by m, then the function evaluated at the center is also bounded by the same m. Okay, so that's the property from the boundary to the center.